Good. So what we do today is talk about phase separation in liquid mixtures. This will cover the thermodynamics of liquid mixtures that some of you may already know, but it also will cover the dynamics of liquid mixtures. And before we start with the mathematical analysis, let me give you a kind of a small introduction. Yeah, liquid systems are quite important because the past is solid and the future is liquid in a way. So what we would like to ask is, if you do have different mixtures, liquid mixtures, and you combine them, for example here in a binary system where you have a liquid of type A and type B, and if you put them together, what happens? Do they mix? Do they unmix? What kind of dynamics do you get? What's the process of mixing and demixing? All of those questions. These systems are quite important because they cover a lot of systems in in soft matter physics and in physics of living systems. You can think of mixtures of water and oil. That's a quite, everyday experience example, and you have all seen the mixing of water and oil. Water and proteins is more at the scientific side, where you really want to know in a cell where you have water and lots of proteins, how is it that these systems have function despite the fact that you have all these different phenomena that would mix or demix water and proteins. And also you can have polymers. These are elongated structures, and you want to know if you mix two different types of polymers, what happens then? Right, so you want to know what is the emergent thermodynamic stable state as you mix those, and how do you reach the thermodynamic stable state? I mentioned it a bit already. One really basic motivation for studying these systems is biology, especially the physics of living cells. Here this is an artist's view of a living cell, and you can imagine this is a very, very crowded environment. It's not just water and a few things, it's really water and a lot of different things. You have membrane proteins that make up the membrane here, lipids, you have DNA, you have mRNA, you have tRNAs, you have all kinds of different proteins that are making up this very mixed crowd of soft material. And very recently there was a striking observation by Cliff Brangwyn and co-workers that was published some time ago now. But in the meantime, this whole thing has grown into a major field in biophysics and in biology in general. And the observation is that in a cellular context, you not just have organelles, but you have these little dots that you see here, and these are droplets. They don't have a shell like an organelle that's composed of lipids. It's just liquid droplets, and those systems are argued to play an important role in the regulation of biological phenomena. And that's why people have been starting experimentally and theoretically to study the physics of liquid-liquid mixtures, either in a thermodynamic sense or by activating them by some kind of fuel that drives these systems out of equilibrium. And here when I run the movie, you see these liquid droplets. They organize themselves at one side of the cell, so they somehow reflect the polarity of those cells. And and you want to know, why is this happening? What's the size of these droplets? Are they stable? Do they coarsen? Are they nucleating? Are they coalescing? And many other questions more. So that's my basic motivation. And now let's go and study this in detail. And I will start with just the thermodynamics of multi-component mixtures. It really means what's the equilibrium behavior of these systems. In general, you want to know what is the behavior of systems with a certain number of components, and I write it as n plus 1 because I want to distinguish between the solvent and the solute, and the solvent is always the 1. The solvent typically is water. Okay? And the case we are most interested in is a binary mixture where you just have n equal 1, and this is then composed of a solvent, usually water, and a solute, so some kind of particle, which could be a protein or a colloidal particle or a polymer, etc. So some kind of either small or mesoscopic or even macroscopic type of particle that's suspended in some kind of fluid background like water. Now in thermodynamics, what we do is we characterize things in terms of macroscopic quantities like the temperature. So let's say we have a given ambient temperature that we want to keep fixed, spatially uniform and not changing in time. And you also may have an ambient pressure in the system that defines forces acting on the whole volume. And the more important variables are the Ni, meaning the number of particles of species I. So let me say this is the number of molecules of a given species I. So once you have that, we have all the macroscopic quantities that are sufficient to characterize a thermodynamic state. And we characterize then the thermodynamics of that state by Gibbs free energy. And this Gibbs free energy will be a function of its natural variables, which are temperature and pressure. So that's the typical natural parameters you have when you consider a chemical system where you keep the temperature fixed and you are at atmospheric pressure, for example. And then you also want to specify all the different particle numbers that you have in your system. Right, so polymer type 1, type 2, type 3, etc. Now, as you know from your introductory course in thermodynamics, the differential of the Gibbs free energy is minus the entropy times the differential in the temperature plus the pressure plus the volume times differential in the pressure. And then I have, and those are the key variables, a sum from 0 to n. And here I do have the chemical potentials and the differential of the number of molecules of species I. Good. Now, this is something that we need to analyze in very general terms to understand the thermodynamics without even specifying the molecular interactions in detail. That's just the framework coming from thermodynamics alone. And now let me define a few things. One are the molecular volumes of your particles. And now let me specify to S and P, meaning really here my solvent that I call S, and the solute, which is not just the one component, that I call P. So think of P as particle. just two components. And then I define the molecular volume of my particles, of the solute, as the partial derivative of the volume with respect to the particle number of the solute. And I'm keeping things fixed. What I'm keeping fixed is the number of solvent molecules, the temperature, and the ambient pressure. In the same way, I define the molecular volume of the solvent as the derivative of the total volume with respect to the solvent number of particles. Now I'm keeping the solute particles fixed, and as before, I keep temperature and pressure fixed. Okay. If you have it like so, then you know that your volume is extensive, right? If you take the volume, fix temperature and pressure, but you increase the number of solvent and solute particles by a constant amount, just some factor, then you know because your volume is extensive, it will increase by the same factor. So this will be the scaling factor alpha times the volume Tp ns np. All right, so as you have extensivity of the volume, you can use this, take a derivative with respect to alpha, and then you immediately see, using these relations here, that the volume that we have for such a system is the molecular volume of the solute times the number of the solute particles plus the molecular volume times the number of the solvent molecules. It sounds like obvious that you write this, but in general, if you look at a thermodynamic system like so, Vp and Vs are in general functions of temperature and pressure. So this is not such a trivial relation as you might think. But still, you should intuitively just think of this as the total volume is made up of the proteins or the particles and the solvent. In the following, I would like to look at a very particular case, namely that our system is incompressible. Okay, so consider an incompressible system. And with that, what I mean is that these molecular volumes are constants. Independent of temperature or pressure. All right. Now, once you have that, then you start realizing that now that I have this incompressibility condition, that the volume no longer is an independent variable because it's determined, as you can see here, given those molecular volumes, just in terms of the particle number. Right? Once you specify them, you know the volume. And that I need to account for in the thermodynamics and rewrite the free energy correspondingly. So let's, for that, consider the free energy, Tp, Np, Ns. And as you know, that's related by a Legendre transform, where you add P times the volume, and then you get the Helmholtz free energy, which is now a function of T and V, and NP and NS. And the free energy is a more convenient thing to work with in an incompressible situation, because then you can write that this, by the extensivity also of the free energy, we'll see this in my notes as a tutorial, that this is then given by a volume factor, the pressure plus the free energy, and this free energy then is only a function of temperature and a quantity phi, which is the volume fraction. So with phi defined as the volume fraction of my solute particles, so the number of those solute particles times their molecular volume divided by the total volume of the system, that we call the volume fraction, right? And the volume fraction obviously then of the solvent is 1 minus this phi that you have here as the volume fraction for the solute. And that means this is now an independent dynamic or thermodynamic variable. Phi, the volume fraction, and the temperature, these objects here are fixed externally. Okay, and our F is a free energy density that we work with. All right, now let's talk about the thermodynamics of mixing here, given this general framework. And the first thing we want to know is what are stability criteria for thermodynamic for mixing. So thermodynamic stability and mixing criteria. So what we want to know is we have, say, a certain volume V1 that contains a volume fraction of solute particles phi1, and you combine it with a second volume that has another volume fraction of my solute particles, and you combine them. So you try to mix them together, and then as you mix them together, you will get a larger volume V with a certain volume fraction phi. And we want to have criteria under what conditions can I do this? Under what conditions will this system here mix into a homogeneous solution of the two? Or the other way around, under what conditions would a homogeneous solution demix and phase separate in two different concentrations, volume fractions, phi1 and phi2. All right, so for that system here, on the left, we do have a free energy F of phi1. For that, we have a corresponding free energy density F of phi2. And here we have a free energy F of phi. And what we want to learn from the thermodynamics is under what condition is the weighted sum of these free energies larger or smaller than the free energy density that you have there. And that will give you then inform you about stability of either one. So let's do that. So for that, we first need to look at the constraints that we have. We have incompressibility. That means the total volume must be the sum of the volumes of the two systems that we look at. So V1 plus V2. And in addition to volume conservation, we have particle number conservation. Particles are not lost here. They're not created. They're not destroyed. And when you look here, what's the particle number? The particle number is phi times the volume. Okay? So what I need to have is that for particle number conservation, I need to have that particle number of solute particles in the mixed system needs to be the same as the sum of the particle numbers in the two separated system V1 and V2. Right? Yeah?
But here we have also this volume, molar volume, the definition of phi.
Oh, okay. Thank you. So I'm assuming here, thanks for noting this, I forgot to say that the volume Vp equal Vs equal V. That's what I'm assuming here. If you don't, you have to write this differently. Okay? That's a simpler case that just simplifies my analysis, but not changes things conceptually. And that's what I want to do, to make things as simple as I can. Thanks a lot for saying that. All right, now we have that. And now we want to know what is the stability criterion. So for that, let's define a quantity I'll use later on. I want to know the fraction of volume of my system 1. So this is V1 over V. Then having defined it like so, my total volume fraction is phi 1 times x plus phi 2 times 1 minus x. Okay. And now the criterion for stability or instability is a criterion on free energy. So if we have that the total free energy, and I only need to look at this here now because that term here is constant. So the total free energy of my system, the mixed one, if this is smaller than the free energies of the two components, 1 and 2, well then the mixed system is the thermodynamically more stable configuration, so I will mix. Okay? That's our mixing criterion. And we can formulate it also in terms of the corresponding free energy density alone, using our definition of the fraction of volumes, x V1 over V. So as you rewrite this, I can write this as f of phi, and now let me write phi as this linear combination. So as phi 1x plus phi 2 1 minus x. Okay. This has to be then smaller than. On the right-hand side, I divide by the volume, so this will be x times the free energy at phi 1 plus 1 minus x, the free energy density at phi 2. And that you know, right? This is a very standard criterion in analysis. It says the assumption that this is the condition that the function here must be convex. Okay, so convexity of the free energy density is the criterion for a system to mix. And of course, you can also write this as f double prime of phi greater than 0 for the domain of phi's between phi 1 and phi 2. That's the very same thing. Okay. On the other hand, if you violate that criterion, so if you have something that's concave, then you will have instability. So graphically, this is the following. So let's say you have a free energy that looks like so. It's a convex function. Then as you have here something which has phi 1 and phi 2 here, then the system has a lower free energy if it's going to a homogeneous steady state. On the other hand, if you have a concave form, element of free energy, and again, let me draw this chord between phi 1 and phi 2. Now the opposite is true. If you start out from a homogeneous concentration like so, you will go down because now the chord has the lower free energy. Right? So it's always this, what is the lower free energy? The mixed system or the demixed system, and the demixed system by this here is a chord which is spanned by this line. This is, it will mix, and here it will demix. Okay, now we know when things are unstable, but we don't know what the corresponding phase then looks like. So given the free energy density, how would I now construct the corresponding values of phi 1 and phi 2? What would they be, and how should I compute them? That's the next question we ask. And this is a very famous construction. It's called the Maxwell construction. And from the Maxwell construction, we then also directly get the equilibrium phase diagram. It's a very beautiful thing because geometrically, by just looking at geometric properties of the free energy landscape, you can immediately infer what the steady state is, and you can draw the phase diagram. No calculation needed, just looking at the geometry. So how would I do that? Well, let me draw a free energy density. So here I'm drawing the free energy density as a function of phi. And you've seen free energy densities. We talked about the Ginzburg-Landau model for ferromagnets that has either a parabolic shape or a double well shape. Now that we have a fluid where you again have a scalar density phi, we no longer have this beautiful phi to minus phi symmetry that we have in the Ising model, right? Because there's no up-down symmetry in a liquid. Moreover, this variable phi is positive, so I should better draw it on the right-hand side. Phi should be greater than 0. It's a volume fraction. So I can draw basically any function I like that could define the free energy density of a fluid, of a binary mixture. And let me draw one that looks like so. So here, let's say I have a minimum. Then it goes up, and it goes down again. Right, so it has two minima, it has one maximum. And now we need to define, from what we just learned, what the different regions are here in our geometric representation of the free energy landscape. So what do we have? Here, between these two inflection points, this one, and I guess it's basically this one here, right? So those are two inflection points, and they define the region where our free energy density is concave. That's the concave region. And that means in between those 2 points, here that we call phi A star and phi B star, the system is unstable to any small perturbation. That's what we just showed. When it's concave, spontaneously the system will demix because the free energy of a demixed state has the lower value. These 2 points that I just drew, phi A and phi B, they are defined by inflection points. That means the second derivative at phi A star is 0 at both of these points. And they are called the spinodal points, or later the spinodal line, giving the boundaries of the region where you have spontaneous phase separation. And so between these points, phi R and phi B, you have spontaneous phase separation or demixing. Okay, so starting from any point here, in between those two, you will demix. Where will you go when you demix? And you will have to go to a system that's given by a chord, by a line. So you have to go down and down until you reach a point you can't go any further. Right? And that's the common tangent that you can draw along this free energy landscape. That will be the equilibrium steady state. So let me draw that. I hope I can draw this properly. So this is the common tangents that you have, which will be the defining line for the demixed state. What's the condition for that? Well, the condition for the common tangent is that the tangents are the same, the slopes are the same. That's one condition. So I have here these points. Those are not necessarily the minima, right? Be careful. This is not the minimum necessarily, so phi B, and this here is phi A. So I need to have the same slope of the free energy landscape at phi A and at phi B. But those slopes need to be on the same line, right? And for that to be on the same line, I just need to have that the line I construct from here with the slope phi, f prime of phi A has to meet the line I construct from here with the slope f prime of phi B. And that means that I will have the function at phi I minus phi A f prime of phi A is the same as the function at phi b minus phi b and the slope at phi b. Okay. Those are the two conditions. Those things have to be equal for the system to be in a equilibrium steady state. Yeah.
So could you again explain why do we choose this condition for the mixed state?
Because the mixed state here is composed of one system that has composition phi 1, the demixed state of phi 1, and the other one that has composition phi 2. And the free energy is additive, right? And therefore, the free energy of a demixed state is a linear combination of the free energies of the two demixed components weighted by their corresponding fraction, just as I wrote it here, right?
I understand that we need to choose 2 points from this curve, which will represent two demixed phases,
Yeah.
and to like connect them
Yeah.
with a line.
Yeah.
But why with that line and not, for example, a chord?
Because then you cut. If you do a chord, I can still go deeper. So I need to find the minimum of the free energy of the demixed state. And this is how far you can get. If you go higher, you have a higher free energy. That's the lowest point you can get. That's a very simple argument. Just to minimize the free energy as low as you can go, and then you're done. And that's necessarily the convex hull of the free energy landscape. Okay, so you don't need, and that's the beauty of the argument, you don't need to argue that some kind of chemical potential or some kind of pressure is the same. That's all not needed in this argument. It's just based on the geometry of the free energy landscape, nothing but that. We'll come to an interpretation of this criteria in terms of some thermodynamic variables in a minute, but for now, and that's very important, the geometry of the landscape is the only thing you need. So this is the construction, and that's due to Maxwell. Okay, so let me emphasize, it's a geometric construction of the thermodynamic stable state. So we did not finish yet what we needed to do. So I do have this region that we already talked about. But there is some other regions that we have here. And these other regions that you have here are the ones that are beyond phi A and phi B, to the right of phi B and to the left of phi A. And we have those regions in between. So the region here, sorry, this one and that one. Okay, there we clearly have something that's convex. So it's stable for local perturbations. But if you perturb strong enough, you can still go down to this red line here. That's the thermodynamically stable state. So any state, any concentration in between phi A and phi A star, or phi B star and phi B, they are metastable. And the ultimate thermodynamically stable state is the demixed state. That's a metastable region. And these 2 points are called the binodal points. in those regions here, then define the metastable regimes. Outside, right, there's nothing I can go down to. When I have a volume fraction that's here or there, then these states are thermodynamically stable states, so the system is fully mixed. And now that you have that, you can construct a phase diagram from that. And the way you construct the phase diagram is that you now vary the temperature, which is one key thermodynamic variable. And as you vary the temperature, this landscape will change because the free energy density, remember, F is parameterized in terms of temperature and is a function of phi. So like in our case of a ferromagnet, the temperature would change the free energy landscape from a parabolic case to something that has two equally sized minima. And here you can imagine the same thing. As you change temperature, your free energy landscape will change in a way that these two minima, they might get, weaker and weaker, and you get landscapes that look like so, and ultimately are landscapes which are just convex and have no concave parts anymore. And the point where you lose the concave parts in your free energy landscape is the point where the system cannot phase separate. So as you imagine changing temperature in this way, right, the landscape changes, and you will get a phase diagram that accounts for that, such that we have a region in phase space which is defined by the binodal, such that outside you have a one-phase, well-mixed region, and inside you have two-phase coexistence. So here we have one phase. Here we have two-phase coexistence. That point here is a critical point. Beyond the critical point, there is no there's no phase separation anymore. And within the binodal, so as here, there is the spinodal, and they meet here at the critical point. And in between, right, this is spontaneous phase separation within the spinodal, and between the spinodal and the binodal, you have the metastable states, and you need some large enough external perturbation for the system to demix. The critical point here, this one, is actually, and you can check this for yourself, the one where the second derivative and the third derivative are both 0. And what we would like to study, and that's after the break, so what happens to the system as you go through that phase diagram? Dynamically, right? Statically we know. We've already shown this. If you go through and wait long enough for the system to relax back to thermodynamic equilibrium, we know if we are in this green regime, the system will spontaneously demix and form a demixed state with concentrations phi1 and phi2. In the regions which are here in orange, you need an external perturbation large enough for the system to demix, and it stays homogeneous outside. Question though is how, right? If you have a homogeneous mixture and you quench down in temperature or change the volume fraction, typically you would quench down in temperature, you want to know how this phase separation actually happens in space and in time. Does it immediately form such a big droplet in a big droplet within a background? Or are there first many droplets emerging and then there's some coarsening and the system relaxes back to the thermodynamic state only after a while? And the latter is actually true. Okay. Questions? Yeah?
So if we start with a two-component system with a homogeneous, which is a homogeneous mixture.
Yeah.
And we fix P in such a way that we have a diagram like that with two minima and one maximum.
Mm-hmm.
The initial state will be a curve, a tangent that intersects the function f only in the maxima or in one minima, right?
So, I mean, if you have this particular situation that I drew, and your average concentration is, say, somewhere here, just for example, then the system will spontaneously demix into a completely demixed situation where the concentrations are given by the values that you have down there.
And at the beginning, the initial line that intersects the f function just touches the curve on one point.
Initially, you define the volume fraction, phi, right? This is the number of solute particles that you have in your given solution. And say you fix the system to be homogeneous by construction. And then you watch the system as it demixes, and then it will go to a thermodynamically stable state that's defined by the common tangent construction. And it's the intersection points of the common tangent construction with the free energy landscape that give you the concentrations in the two regions of the system. And one has then a low concentration here on the left, and the other one will have a high concentration on the right. Right? That's what happens. And we want to learn how this happens. Yeah?
We said that if we increase the temperature, the concave part kind of flattens and we kind of lose the opportunity to have phase separation.
Yeah.
If we decrease the temperature, we start actually decreasing the temperature. Can we get more concave parts or have more, let's say, weird kind of curves?
Yeah, you can get all kinds of weird curves. It really depends on the system that you study. If you look at a system, and we'll do this later on, that has just pairwise interactions, then the structure of the free energy is typically like so. You will not have more minima than that. Right? If you want to have more minima, you need to add some additional physics that would allow you to have, these kind of minima corresponding to some kind of underlying physics that promotes that minimum. And here the picture is things want to, so you have solid and solvent, and you have a demixing between solid and solvent, so naturally you speak about two different states, a dense state and a less dense state, a liquid and a vapor, a A-rich and B-rich phase. And those are the two minima. And if you think about a third minimum, there must be something more than that in the interactions between the particles. From symmetry alone, of course, you can draw anything you like.